Hi, it's Matthew Reed here, and I'm making another lockdown video, this time about this clock. The clock is early 20th century, homemade electromechanical device based on the Hipp Toggle principle. The treatment, and importantly the thinking about the treatment, I'm going to break down into three distinct areas. That is the electromagnetic coils that impulse the pendulum, the Hipp toggle switch, and then thirdly the mechanical movement that's driven by the action of the electromagnetic pendulum. We're going to be adopting a conservative approach to the treatment of this clock. I would like to get it running. I don't need it necessarily to run the whole time. So we'll be looking at the power supply side of things. We'll be looking at corroded surfaces, treatment of historic wiring, and then cleaning of the clock mechanics. There was a fashion, if you like, for making these kinds of clocks at home. The design and instructions for their manufacture were serialized in magazines like Practical Mechanics. This particular clock is signed A.R. Dayson of Sunderland, 1918. So let's open the case and have a little look around, and to begin to think about the kinds of treatments we're going to carry out in order to return the clock to working order. As we approach the clock, we can see that it has an oak case with very attractive medullary rays, and what you might call a traditional engraved, waxed and silvered dial. The way the case is held closed though is a little bit different. We can see here that there are two BA threaded brass and steel nuts which unscrew and allow the case to open. The clock has a traditional cast brass bezel with beveled glass. So here's the dial with its vertical graining, silvered brass, black painted spade hands, so pretty much standard fare for the period. We can see though that the subsidiary seconds hand is presently held on with a piece of blue tack. Inside the case, the dial plate in particular, this wooden board, we see that it's been cut away. The previous owner told me that at one point the clock had a quartz movement fitted, and luckily maybe the original, or what we believe is the original movement, was kept with the clock and reinstated it, but never got it running. So it'll be interesting to see how we get on in that respect. The electromagnetically impulsed pendulum lifts this crutch pin here, which you can see is loose, rotating the crutch around the pivot at the top, and fixed to the crutch is a pawl which engages with a wheel that's rather like an escape wheel in a mechanical clock. So each time the crutch moves backwards and forwards, it indexes 2 seconds. So when we look at the pawl on its riveted pin, we can see that there are two small drilled holes that should have pins, because what happens if the crutch gets moved to one side, then the little gathering pawl falls out of engagement. So another job on our list is to reinstate those pins. When we turn our attention to the suspension spring, we can see it's kinked, which might result in the pendulum failing to oscillate in a nice clean plane. I put this piece of paper here so you can see, and in slow motion we see a little bit of deviation from that plane. Given that this pendulum is going to be impulsed by a toggle which is offset, maybe that isn't particularly significant, but we'll have a look at the suspension spring and see if it can be straightened, and of course check for cracks and other damage. Moving on to the Hipp Toggle switch. There are two terminals where our current enters and exits the switch. The switch spring is horizontal here, and just about hidden behind the pendulum you may be able to see the little block with which the Hipp Toggle engages with its notch. We'll see this in further detail in a subsequent video. Of course, to note here is there's quite a lot of corrosion around the wires, which are themselves particularly fragile. The same applies to these two terminals where power originally came into the clock. Now here's the Hipp Toggle. The reason it wasn't in view before was because its little mounting screw or securing screw is missing, so it just falls down the pendulum rod. And finally, turning to the electromagnetic coils. You can see the coils are wound with copper wire, which is insulated with silk, which to a degree has degraded. There are a few losses, and the coil that's at the front of the clock, the top few windings have come loose as well. So a couple of things there that immediately need our consideration, and that's where we'll be looking in our next video. So there we are. We've had our preliminary tour of the clock and looked at a few of the areas that might need thinking about and addressing in treatment. Some of the electrical connections, there's quite a lot of corrosion, and I think this probably happened much earlier in the life of the clock. As we saw, the case is oak, and I wonder whether acetic acid from the oak has caused a lot of that corrosion. That may have been decades ago. We don't know what the storage conditions for the clock were. Maybe more dampness, higher RH than we experience now. So I'm not particularly bothered about corrosion moving forward. I think that most of the damage that is done has been done. However, where we want to establish good electrical connections, we'll have to deal with that, and we'll maybe consider removing some of those corrosion products because they could cause further problems in future with these objects. We're taking a relatively conservative approach, so I'm going to do what I feel is the minimum treatment necessary to get the thing into stable working order. And of course we can always monitor. This is once we've carried out our treatment, we've done our treatment report, we'll be able to monitor on an ongoing basis and keep an eye on those areas of corrosion for possible further consideration. So of the three primary areas of this clock, the mechanical movement, the Hipp Toggle switch and the coils, we're going to look at the coils first.